Okay, good morning, everybody. Let's get started. Okay, the first order of business before we start our topic is we're going to talk about the exam. So we have two choices for the exam. We can have it on Monday, we can have it on Wednesday, and we can have it in class exam and see all these missing people, or we can have it a take-home exam. Do you want to vote?
Take home.
Take home. Any strong opposition to a take-home exam?
No.
But you're a minority, like your vote will not even, if I added all your votes, we still do not have the quorum.
What happened to Huntsville?
Well, there's probably half the class are like watching online. Okay, we'll do a take-home exam. Wednesday
Do Wednesday or release Wednesday?
or at release Wednesday? Or
Okay.
do... Okay, so we'll have our...
This is the last exam.
potentially.
You do really good on it, and you do really good on the first one. You don't have to do the third one.
And it will be March 29th.
Do
Sounds good? And last time we gave 24 hours.
yeah.
So we'll do this probably something similar, 24 hours to turn it in. Okay.
So do we have class that Wednesday?
Yeah, we will have a class. And since we have two classes, potentially we can, if we choose to, finish like a week earlier before the end of the semester. Or maybe we'll use it for the project. We'll see. But that will give us like 2 extra classes. Okay, so in the previous class, going back to what we've been doing, if you remember, we were designing filters. And we reviewed the design of a continuous filter. We looked at the Butterworth and Chebyshev, and we mentioned the elliptical and Chebyshev type 2 filters. But then we said we are interested in building a digital filter. So what we said we're going to do is we're going to be, after we reviewed these analog filters, we're going to transform them into the digital domain. I said we're going to look at 3 different methods of taking an analog filter and change it to a digital domain. The impulse invariance, the match C transform, and the bilinear transformation. And then also we said that in doing so, we're going to make sure that we preserve stability, we preserve the frequency response as much as possible, we want to avoid aliasing, and we want the transformation to be as simple as possible. And we start looking at the first method of transforming an analog filter into a digital filter, and that is the impulse invariance. So the idea is that if I build the analog filter and I have the analog filter frequency response here, I can go back and take the impulse response of that filter. This is what the impulse response will look like for that filter. Then I can come here and convert it to a discrete time domain by sampling this filter. And if I sample this filter, what's going to happen? I'm going to get the frequency response, the original frequency response, but also, in addition, I'm going to get this alias version of that filter. Does that make sense? Because this graph is exaggerated. If this is repeated and the aliasing is less pronounced, then I have the same shape, or I have the filter shape that I'm trying to achieve. Does that make sense? So with that, we're going to continue our discussion using the impulse invariance method. And let me just copy the graph from the previous lecture. Okay.
That aliasing is because, by definition, it's an infinite. It's an IIR. So, like by definition,
No,
Because
it's
of your sampling frequency. Because of your sampling frequency.
IIR has an infinite impulse response. Has nothing to do with aliasing. Or it's not, it's different than aliasing. Aliasing is in the frequency domain. IIR, in the time domain, the impulse response goes to infinity. Does that make sense?
yeah.
The two? So I can have an IIR filter that is much sharper, and it might not have an aliasing. So if this filter, frequency response, for instance, was like this, then I'm not going to have aliasing. I'm going to repeat it here. I'm not going to have aliasing. Aliasing comes from the sampling of the impulse response. Does that make sense? This sampling is going to get the replicas, and depending on how fast you're sampling, you can increase the aliasing or decrease the aliasing. Makes sense? If you sample at a higher
You're
rate,
saying you would have aliasing no matter what.
you might have aliasing. You will have aliasing if you're sampling. The impact of the aliasing will depend on how fast you sample. Increase the sampling rate is going to remove that replica, and since it is going down, the impact is going to be reduced. Okay. So therefore, looking at the impulse invariance, we're going to get the frequency response of the continuous time filter. We're going to take the impulse response of the filter. We're going to sample the impulse response of the filter. That is going to give us the h of n, the impulse response in discrete time domain. And from h of n, we can get h of z. And again, that problems with the fundamental problems we have, fundamental problem that we have with the impulse invariance is the aliasing. Sampling of h of n, of hc of t, the continuous impulse response, is going to result in aliasing in h of e to j omega. Remember, h of e to j omega is equal to 1 over t, the summation of the continuous j of omega minus 2 pi n divided by t, and we replace omega with omega over t. When we sample, the spectrum is going to start repeating, and that repetition is going to result in the aliasing. Okay. Now if you look at how the frequencies from the continuous time domain to the discrete time domain are mapped, we can see the impact of the aliasing. Okay, so if I were to plot the frequency domain, the S domain, and the Z domain, and see how different frequencies are mapped. So this is our Z plane, and this is our S plane. So if I have a frequency, what does this axis represent? J omega axis, sigma and the J omega axis. So along the J omega axis, if omega is equal to a 0, what frequency will correspond to in the Z domain, in the Z plane? A 0. Omega is equal, if omega is equal to 0, Z is going to equal to a 0. So here, this frequency here is going to get mapped to this frequency here, to this point here. remember, omega is equal to W multiplied by T. And if I am at this point here, what is omega equal to? At that red dot there? 0. Omega equal to a 0. Okay. If I increase my frequency, and now I am operating at pi over 2t, what is that gonna map to on the unit circle?
The other side of the circle.
It's gonna go to pi over 2. Therefore, it's gonna map to this point here. Agree? Again, pi over 2 times t is going to be pi over 2t times t is going to be pi over 2. If I increase the frequency, and now I'm working at this frequency, the pi over t, then this is going to get mapped to this frequency, to this point on the unit circle. Pi omega equal to a pi. Now, similar thing happens in the negative frequency. So if I am at negative pi over t, I'm going to get mapped to this point here. And if I'm operating at negative pi over 2t, I'm going to be operating at this point here. Together? Does that make sense? Again, coming from omega equal W multiplied by T. And this is our omega. Okay, what happens when I map frequencies that are beyond this range? So I have this range here that we mapped. And this range, as you can see, will cover the whole unit circle. In this range, if I take any other frequencies, I'm going to be covering the whole unit circle. What happens when I take a frequency that is outside this range? It's going to go back to a point that is already mapped. And therefore, this is what we see with the aliasing. So if I come here, for instance, and take a point here that is 2 pi divided by t, this point is going to get mapped back to the same point that I mapped the 0 frequency to. And similarly, if I take a 3 pi over 2 over 2t, then this is going to get mapped to the same frequency that already mapped the negative pi over 2t. And this is what we see with the aliasing. This is basically what the aliasing is. Okay. So therefore, let's see what happens if we have a low-pass filter and if we have a high-pass filter. And we are trying to use this method for designing the filter. Okay, so here we designed a low-pass filter. This is a Butterworth filter, a Chebyshev filter, whatever filter we designed in the continuous time domain. So this is W, and this is our filter. Now when we map this and we sample the impulse response, what's going to happen to this filter in the frequency in the discrete time domain? We're going to have this filter that the original frequency response, and in addition, we're going to start to have repetition of this spectrum. I'm going to have another repetition and so on. Is that clear, everybody? Sampling the impulse response is going to give me a spectrum that might look like this. Now what happened here? Aliasing. And this magnitude is 1 over t. Okay. So So therefore, the filter in the discrete time domain is going to have the same almost shape as the low pass filter, but it's going to also have an aliasing added to it. What does that mean? The filter that we're going to be building might look something like this. We designed it to look like the black one, but instead it might look something like this. Where is this coming from? From this aliasing. Now let's see what happens if we designed a high pass filter. So this is our the frequency response of the high pass filter. We took the impulse response, we sampled the impulse response. Let's see what's going to happen in the frequency domain. What's going to happen in the frequency domain? We're going to have the original shape. And now we're going to also have the repetition. So let's say at 2 pi, we're going to have this shape repeats. At negative 2 pi, this shape is going to repeat. What's happening here? The aliasing is distorting completely, destroying the filter. Does that make sense? When I look here, I want this to suppress all the frequency, the low frequencies, because it's a high pass filter. But look, because of this alias signal that is coming, now all of a sudden that frequency is going to pass through. Does that make sense, everybody? So therefore, what do we conclude? Even if you sample more, it's not going to make any difference. Even if you move that replica, this is going to go to from negative infinity to infinity. Make sense? So can we use the impulse invariance method to design a high-pass filter? We cannot. So the impulse invariance is limited to low-pass filter and band-pass filter. We cannot use a high-pass filter, and we cannot use a band-stop filter. Is that clear? And this is the reason why. Because of the aliasing is going to distort the frequency response to the extent you're not going to get the characteristics that you intended to. Okay, so with that, let's look at the design step for designing an impulse invariance filter. So from the specifications, we're going to design HC of S. So again, a Butterworth, a Chebyshev, any filter that you like. After we design the filter, after we have HC of S, we're going to write HC of S as the summation of AK divided by S minus SK from K equal 1 to N, where SK is a pole of the system. So I'm going to do partial fraction expansion. I'm going to express the frequency response in this form, expanded around the poles of the system. Now then I can get the impulse response of this filter, HC of T. What is HC of T going to equal to? It's going to equal the summation from K equal 1 to N. AK, what is the inverse Laplace of AK over S minus SK? Is going to equal to E to the power of SK multiplied by T. Together? So this is what the HC of t is going to equal to when t is greater than 0, and it's going to equal to t to 0 when t is less than 0. So we have a causal filter. This is the impulse response of that filter in the time domain. What is the next step? We're going to create h of n, which is going to equal to hc of n multiplied by t. What is this going to equal to? The summation from k equal 1 to n, ak multiplied by e to s sub k multiplied by t multiplied by n. So I'm going to replace t with n multiplied by t. I'll be sampling the impulse response. Is that clear? Makes sense? Okay. Now that we have h of n, we can get h of z. What is h of z going to equal to? From k equal 1 to n, ak multiplied by z divided by z minus e to the power of sk multiplied by t. So this summation, you can think of it as summation of a constant multiplied by a to n. The z transform is going to be z over z minus a, where a is equal to exponential of sk multiplied by t. Together? And finally, we can set the gain. Okay. The gain, I mean, if we are using, if it is a low pass filter, we set the gain when omega is equal to a 0. What is omega equal to a 0 corresponds to?
0
Corresponds to z equal to a 1. Together?
Yeah.
Omega equal to a 0 corresponds to omega equal to a 0 corresponds to z equal to a 1. If I have h of z, I'll substitute h of z when z is equal to a 1. I'll set that gain to whatever DC gain I want. Okay. So just few notes, and then we'll do an example. If h of c, hc of s is stable, that means the poles of sk are less than 0. They are in the left half plane. And that means the magnitude of e to sk multiplied by t is going to be less than 1. Together? So if the system in the continuous time is stable, is it going to be stable in the discrete time domain? It's going to be stable because sk is going to be negative. And exponential to a negative number is going to be less than 1. And if it is less than 1, it's going to be stable. Why is it going to be stable? Anybody?
The poles are not on the circle.
Yes, because the poles are in the unit circle, and this is causal. So the regional convergence is going to be outside the largest pole, therefore it's going to include the unit circle. Okay. The second observation, we're going to have linear frequency mapping in the range when omega is greater than negative pi over t and less than pi over t. And we're going to have aliasing outside of this range. And again, this comes from the graph that we've done in the previous slide. The maps between negative pi over t and pi over t will map to the whole circle. Anything outside is going to go back and give us aliasing. Another observation is that the poles are mapped. The sk, the pole that is in the continuous time domain, is going to be at exponential sk multiplied by t. This is s sub k. Okay. And because of aliasing, the sampling frequency will have a huge impact on the filter. And finally, we can only design a low pass and band pass filter. Okay. Any questions? Okay, let's do an example. Okay, so in this example, we're going to design a low pass filter, and we're going to design method is impulse invariance. And the filter type, we want to design a Butterworth filter. And the specifications for this filter are the following. The sampling frequency is equal to 40 kilohertz. The cutoff frequency is equal to 2 pi multiplied by 8,000 radian per second. And the stop frequency is equal to 2 pi multiplied by 16,000 radian per second. And the attenuation, stop band attenuation is 10 dB. So therefore, we want to build a filter, and according to the specifications, this filter should look something like this. This is 0 dB, and the 3 dB is at 2 pi multiplied by 8,000, and at 2 pi multiplied by 16,000, we want the attenuation to be 10 dB. So this is going to be negative 10 dB. And this is H effective of W in dB. Together? Okay. So what is the first step? We're going to design the analog filter. So we're going to determine the filter order. And the filter order for the Butterworth filter, we're going to take 10 log 10 of 1 plus omega stop divided by omega cutoff to the power of 2n. We want this to be greater than or equal to 10 dB, which is the attenuation. And therefore, if we plug in when n is equal to a 1, we're going to get 6.989 dB, which does not meet this equation. If I take n equal to a 2, this is going to be 12.3 dB, and therefore the filter order has to be a second order. What do we do next? We're going to go to the tables, and we're going to determine Hc of S, the frequency response of the filter. The table is going to give us the normalized Hc of S, and from the table this is going to equal to 1 over S squared plus square root of 2 multiplied by S plus 1. And we can write this in a factored form. This is the same as S plus 1 over square root of 2 plus J multiplied by 1 over square root of 2 multiplied by S plus 1 over square root of 2 minus J multiplied by 1 over square root of 2. The next step, we're going to unnormalize. How do we unnormalize the filter? We're going to substitute S with S over J omega C. So Sc of S is going to equal to 1 S over 2 pi multiplied by 8,000 plus 1 over square root 2 plus J multiplied by 1 over square root of 2 multiplied by S over 2 pi multiplied by 8,000 plus 1 over square root of 2 minus J multiplied by 1 over square root of 2.
That's the sample?
No, that's the omega C. Unnormalized. The filter in the table have omega C equal to a 1. So to unnormalize it, you replace S with S over omega C. Okay. What is the next step? We're going to do partial fraction expansion. So therefore, we can write it, and we are missing, we are not missing anything yet. We can write Hc of S as equal to 2 pi multiplied by 8,000 squared divided by S plus 2 pi multiplied by 8,000 multiplied by 1 over square root of 2 plus J over 1 square root of 2 multiplied by S plus 2 pi multiplied by 8,000 multiplied by 1 over square root of 2 minus J multiplied by 1 over square root of 2. We got that? So we just multiplied the numerator and denominator by 2 pi multiplied by 8,000. Now we can expand this. This we can write as 2 pi multiplied by 8,000 multiplied by J square root of 1 multiplied by 1 over square root of 2 divided by S plus 2 pi multiplied by 8,000 1 over square root of 2 plus J 1 over square root of 2 plus 2 pi multiplied by 8,000 negative J 1 over square root of 2 over S plus 2 pi 8,000 1 over square root of 2 minus J 1 over square root of 2. Together? Okay. Now we have HC of S in partial form, in partial. Go ahead.
Why is 2 pi times 8,000 squared at the top?
Because there is 2 pi that's going to come from this one and
Oh,
one
right,
from
I
this
see,
one
yeah, I
multiplied
see.
together. Okay. So from this one, we can write h of z and h of z is going to equal to 2 pi multiplied by 8,000 multiplied by j 1 over square root of 2 multiplied by z divided by z minus e to 2 pi multiplied by 8,000 multiplied by negative 1 over square root of 2 minus j 1 over square root of 2 divided by 40,000 plus 2 pi multiplied by 8,000 multiplied by negative j1 over square root of 2 divided by z minus e to to 2 pi 8,000 multiplied by negative 1 over square root of 2 plus j 1 over square root of 2, and this is divided by 40,000.
That's all in the exponent of the e, right?
This is all in the exponent, yes. I mean, this is the all divided by the sampling frequency. Okay. Where is this coming from? It's coming from the design step that we agreed to, isn't it? And once we have this in partial fraction form, then h of z is going to equal whatever ak multiplied by z divided by z minus e to whatever sk multiplied by t. Make sense? Okay. I mean, apparently we like to, we can think of this, we skipped a step. We could have done h of t by taking the inverse and then taking h of z, but we know how to go directly from here to here. Okay. Let me simplify this.
Why isn't there a z on the other side?
Which side?
The numerator, there's a z, you added a z in the numerator here.
Yeah.
Okay, just one, sorry.
No, I just added it. Yes, there is a z there.
Okay.
Like a science. And the 40,000 is from
The sampling.
the same.
Yeah. We multiply by t, which is 1 over the sampling. Does that make sense?
Okay.
Again, this all coming directly, I mean, it's overwhelming when you look at it here, but it's straightforward when you see it here. This HC of, I can write HC of t directly as ek, e to skt, and then I can take the h of z of this directly. This is just a constant to the power of n. It's going to be z over z minus the exponential, that constant, which is the exponential. Okay.
Write the signs of the complex number in the H and Z conversion.
What is it?
Why the signs of the complex numbers flip for the HZ conversion?
Because this should have been, this is positive, e to it's a good question.
SKT?
A negative SKT, yes. SK. That's right. Negative SKT. Okay. So we can simplify this. So this is gonna simplify to h of z equal to k, a constant, we put all these together, divided by z squared minus 0.5186 multiplied by z plus 0.169. Yeah, actually there is not, I'm going to go back. This is positive, but this one, s minus sk, will become the positive of it. This is s minus k, it's going to become the positive of it. If it was s plus sk, it's going to be s negative sk. Make sense? So this is e to sk multiplied by t. Okay. So again, that's why we need a take-home exam. We can go and simplify this, and we're going to get h of z that looks something like this. Okay. What is the final step? Is to set the value of the DC gain. So the final step, we can set DC gain. What is the DC gain? Z equal 1 when omega is equal to 0. Like basically the signal is not changing. And we're going to set the DC gain so that the gain at omega equal to 0 is equal to a 1. And therefore, we want h of 1 to equal to a 1. Together? Where is this one? This is z equal to a 1, which is the same as saying e omega t, and omega is equal to a 0. Okay, so if I want the DC gain to equal to a 1, I can calculate the value of k, and k is going to equal to 0.65. So I can substitute h of n, 1 over 1 minus 0.5 plus 0.169. And I want it to multiply by k to equal to a 1. K is going to equal to 0.65. So therefore, I can write h of z, and h of z is going to equal to 0.65 multiplied by z divided by z squared minus 0.5186 multiplied by z plus 0.1691. How can we implement this filter? I can write this as 0.65 z to negative 1 divided by 1 minus 0.5186 z to negative 1 plus 0.1691 z to negative 2. And what is this going to equal to? Y of n over x of n. What is the equation that will implement this filter? Y of n equal to 0.5186 y of n minus 1 minus 0.169 y of n minus 2 plus 0.65 multiplied by x of n minus 1. And this is my better worth digital filter. Is that clear, everybody? Okay.
Would you suggest that we do all this in MATLAB? I mean, there's a lot of room for error. You didn't show any of the math, right?
Not the trivial math. Doing this to this.
Yes.
That's you can, of course, use MATLAB. I mean, use MATLAB, but be aware that you might also do a mistypo in MATLAB.
Sure.
Now, ultimately, and we will see this in a minute, probably we'll see it in a minute, we're going to do 5 pages of work on this, and MATLAB is going to do this in 1 line. However, in order to understand what that 1 line of MATLAB is doing, you're going to have to understand these 5 pages. Because you can easily, get things that you'll not understand what they're coming from. Sounds good? So what we're going to do is we're going to continue this example, and then we're going to run MATLAB and show how MATLAB is doing all this. Okay. So what we're going to do, just to add to this part, and probably I should show you MATLAB first to convince you we need to do that, but I'm going to trust that you're going to trust that I'm going to show it to you and you're going to agree. And if I were to plot the frequency response of this filter, and if I want to improve on the performance of this filter, what do you suggest we can do?
Increase the order.
Without increasing the order? We can increase the sampling frequency. Although not clear why, but we will see it when we run the MATLAB. But let's, if you like, we can look at what is the impact of the sampling frequency on the filter performance. So okay. Now remember, when we started all this discussion, what we said we're doing is we have an analog signal that I want to filter and generate an output. We said we could do an analog filter, or we can come here and say, okay, I'm going to take this signal, I'm going to convert it, analog to digital converter, do a digital filter, and then go do a digital to analog conversion, and then get you the output. All this, or you can do an analog filter. Make sense? So assuming that we have control over the sampling frequency. So I have built this whole system, so I can control the sampling frequency. I can change the sampling frequency. Does that make sense? But if the signal is already sampled at a certain sampling frequency, then I cannot change the sampling frequency. Does that make sense? If the signal is given to me already sampled, if I'm only controlling this part, then I don't have control over the sampling frequency. Make sense?
Yeah. Upsample or downsample to.
Well, potentially, yes. You can do an upsampling or downsampling to increase that sampling frequency. Yes.
But it's not going to be it's not going to improve your results, right?
Increasing the sampling frequency will improve the result. Yes.
Sure, but without saying if we don't have control of that, and we upsample or downsample, and then do a filter on that data.
But what we're saying is valid. If I have a signal that's sampled at very low frequency, and I increase the sampling of it by upsampling it, then I can have a better filter over the upsampled signal. Make sense? So if you're willing to pay a cost to upsample it, I can give you a better filter. Make sense? If you have control over all the system, you can control the sampling frequency, then higher sampling frequency is going to give you a better filter. Is that clear? Make sense? Okay. So we're going to see what happens if we change the sampling frequency from 40,000 to 200,000. So we're going to look at what happens when Fs is equal to 200,000, and therefore T is equal 1 over 200,000. And if I look at the solution that we've done, the only thing that's going to change, if you look at it, is that h of z is now going to equal to 2 pi multiplied by 8,000 multiplied by j 1 over square root of 2 multiplied by z divided by z minus e to j to 2 pi multiplied by 8,000 multiplied by 1 over square root of 2 minus j 1 over square root of 2 divided by 200,000 and plus 2 pi multiplied by 8,000 negative j 1 over square root of 2 multiplied by z divided by z minus e 2 pi 8,000 1 over square root of 2 plus j 1 over square root of 2 and divided by 200,000. All this is in the exponential. So this is the only thing that changed from the previous if we change the sampling frequency. That's the only place it will show up. Okay, so if I simplify this, I'm going to get k multiplied by z divided by z squared minus 1.648 multiplied by z plus 0.70087. And if I do something similar, where I'm setting the gain for DC to equal to a 1, then K is going to equal to 0.05287. And therefore, H of Z is going to equal to 0.05287 multiplied by Z divided by Z squared minus 1.648 multiplied by Z plus 0.70087. Okay. And I'm just going to put a hint, and then we're going to run the MATLAB, or a tip that you might use. If I have C1 over S minus P1 plus C1 conjugate over S minus P1 conjugate, then this is going to give me H of Z that is going to equal to K multiplied by Z divided by Z minus Z multiplied by alpha cosine omega multiplied by Z plus alpha squared, where e to P1 multiplied by T is equal to alpha e to j omega. Okay. Okay, with that, let's run some MATLAB.
So that tip there, what's useful about it?
What is it?
I don't get what's the tip.
I mean, you can go from this form to this form directly by knowing where the poles are. So if you have you could have gone from here, from this to H of Z directly from this. Does that make sense? this to h of z. This to h of z directly. You know C1, C conjugate, T1, T1 conjugate. You can calculate E to T1 multiplied by T. It's going to give you a magnitude and a phase. And then h of z is going to be of this form. Okay. Make sense? I mean, you can go through the math of finding this is going to be an exponential h of z, exponential h of z, add them together. Eventually, you can show this one. Okay. So let's run the Okay, so this is our analog Butterworth filter that we designed in the continuous time domain. This is our digital filter that we designed with a sampling frequency of 40,000. And this is our filter that we designed with a sampling frequency that was 200,000. And this is the two filters together. This is with the 40,000. This is with the 200,000. Why is there a difference here?
Sampling frequency.
And why is there a difference between the 40,000 and 200,000?
Gain.
What else?
Aliasing.
Aliasing. Yes. Aliasing. Together? So what we're doing, I mean, what is happening here is I build this filter, and then I sampled it. With the 40,000, I'm sampling it, and I'm having the replicas like this. With the 200,000, I have this filter. Now the replica is much, much farther away. And therefore, the impact of it is minimum. By the time, like if I go this far from the frequency, the gain is very small, or the amplitude is very small. It's not impacting the main one. Here, they're very close. They're going to have big aliasing. Okay. So that's why when you increase the sampling frequency, the aliasing is going to be reduced, and therefore you'll have a better filter. What is a better filter? A better filter means I want higher attenuation here. This is the start band.
Yeah.
The more it goes up, then I'm not filtering as good as I want. I want this to be as low as possible. Okay, finally, if I look at the impulse response of the filter, this is the impulse response of the continuous time filter. And this is the impulse response of the digital filter. Because this is sample. I mean, we have two of these. One sample every 40,000, one sample every 200,000. Is that clear?
Yeah.
So is there a Nyquist equivalent for the aliasing here? Because of the aliasing, you might be failing your specs based on your sampling frequency.
That's correct. I mean, you might ultimately not be able to meet the attenuation that you have set. Yes, a good point. So after you build the filter, you have to test it, make sure it is still indeed meeting the specifications. Make sense?
So is this one, so it's 0.3 dB is the cutoff, or what?
Oh, sorry, this magnitude is not in dB.
Okay.
That's a good observation.
Yeah, it's-
This is this in dB? This one is in dB.
That one's also in the.
This one is in dB. Say it again.
The frequencies radians versus the hertz.
Yeah.
Just different frequencies.
Some of them are in radians, some of them are in omega. And this is, nevertheless, is your labeling. You know what I'm saying? MATLAB does not know. But this one, for instance, because it's analog, I plot it with hertz. But then, when it is a digital filter, I wanted to show it with omega. So this is with omega. See what I'm saying? But again, you can you control, and this one should have been with omega too.
That's what I was pointing out.
Yeah, okay. This one was 3, and this should have been omega 2. Okay. Now, having done all this work manually, what does MATLAB need to do all this work? These two lines. What are these two lines? This is going to give you the numerator and denominator of the continuous phi filter. And this is going to convert it to a digital filter. Make sense?
Impulse invariance.
Impulse invariance. Invar. Together? This is the Butterworth filter, second order cutoff frequency. And it's going to give you the numerator denominator. And the second is going to give you the conversion using impulse invariance.
So you can't do that on the homework, I guess.
You can do it if I cannot detect it.
Verify your work.
I mean, do it till you are very frustrated, and then let MATLAB help you. This way you will appreciate MATLAB more, and hopefully you will appreciate the frustration in doing it. Okay, so I'm just going to put one of these figures, and I imagine anybody interested can run this code. Sounds good? Okay.
So,
Go ahead.
so we've been designing only low pass filters.
Mm-hmm.
When are we going to get to the point where we, because like on the first one in the homework, we're supposed to design a notch filter.
A notch filter, we've done a notch filter. This is from the using pole zero method.
Oh, okay, understood.
Yeah, but if there's any high pass, band stop, then we'll cover it later. Together? But nevertheless, we're going to spend time on low pass filter. We're going to spend one lecture on designing other filters. And what does that mean? It means once you design a low pass filter, you can convert it to any other filter. Does that make sense? The conversion is straightforward. Okay. So the next method. Any question on the impulse invariance? Intuitive? Makes sense? Continuous H of S, impulse response, sample it, aliasing, and you have your filter. The next method of conversion is using matched filter, matched Z transform. And in this method, or if you go back to the impulse invariance, basically what we've done is we had poles that got mapped if I have sk is going to get mapped to e to the power of sk multiplied by t. A pole in the s domain, sk, will get mapped in the z domain to e to sk multiplied by t. Make sense? Now if I have zeros, we do not have a direct mapping of these zeros in the s domain, in the z domain. We have not seen zeros in the previous example, but in general, if there are zeros, it will depend on how we're going to do the partial fraction expansion, and therefore where these zeros are going to get mapped. In the match Z transform, both poles and zeros are mapped using sk e to sk multiplied by t. So therefore, if I have a continuous filter, it's C of S, that in general written in factor form S minus Si divided by S minus Pi from 1 to P, then this filter, we're going to map it by mapping the poles and the zeros. So I'm going to generate H of Z, that is going to equal to K multiplied by the multiplication from 1 to Q of Z minus E to Si multiplied by T divided by the multiplication from I equal 1 to P Z minus E to Pi multiplied by T. Okay, so therefore, if I have Si, if I have complex conjugate roots, whether they're poles or zero, they're going to give me complex conjugate roots. And that is, if I have Si in the continuous time domain as sigma I plus or minus j omega I, then this is going to get mapped to Z I equal to E to sigma I plus minus j omega I multiplied by T, which we can write as E to sigma I multiplied by T multiplied by E to j omega I multiplied by T plus or minus. So this is going to be the magnitude, and this is going to be the phase of the root. Okay. So apparently, I mean, if you look at the mapping of the poles, we can see that the stability is preserved. If I have a pole that is in the left-hand plane, then it's going to get mapped to inside the unit circle. If sigma is negative, if sigma is negative, it's going to map to a magnitude that is less than a 1. So therefore, stability is preserved. And similar to the impulse invariance method, this method will also suffer from aliasing. Okay. So again, what is the idea behind the match Z transform? Poles and zeros are just mapped using this formula. A pole or a zero is mapped to e to that pole or zero multiplied by t. Okay, let's do an example. Okay, so we have, in this example, we are given h of s, and this h of s is equal to s over s squared plus 0.2s plus 1. Now this is a bandpass filter, which we have not seen, but we're just going to emphasize the transformation using the match filter. So I'm going to find I'm going to use the match Z transform to generate the discrete time filter. And we're going to assume that the sampling frequency is such that t is equal to 0.5 second. Okay. So what are the poles and the zeros of this system? So we have 0 at s equal to 0, and we have poles that are at poles at negative 0.1 plus or minus j 0.995. Okay, so therefore the zero is going to map and the pole are going to map e to sk multiplied by t. Therefore h of z is going to equal a constant k multiplied by z minus 1. This is e to 0 multiplied by t is going to give me a 1. And then multiplied by z minus e to negative 0.1 plus j 0.995 multiplied by t. Oh, this is divided by t. So this is after multiplying it by t is going to be negative 0.1 plus j 0.995. Is that confusing? Negative 1 minus j 0.995. And therefore, we can write this as k multiplied by z minus 1 divided by z squared minus 1.6718 z plus 0.9048.
So why is T in there?
I'll tell you why. Of 1.2 and 1. Okay, so there is no t in there because multiplied by t. Okay. Okay, let's run. Okay, we'll run it in the next class, the MATLAB that shows the MATZ transform. Any questions?
Yes, on the previous page, I think it was,
Mm-hmm.
what was the coefficient above the product sign?
This page?
It was, at that page, it was when you did the 8C to 8Z, 9C transform page. Okay, so what was that? What's that symbol above the product?
Q.
Q?
Yes.
Okay, okay.
So we have Q terms and P terms multiplied together.
Thank you.
You're welcome.